Okay guys, here is a video on molecular geometry, um, and I'm going to start with the smallest number of things that we can have and then try to go on from there. So to start with, let's say that we had a molecule like carbon dioxide, CO2, and you know what, I might actually be able to go over here and pick some. Yeah. If you do a Lewis structure for CO2, that's basically what it ends up like. Now, just so you can see where I'm coming from on this, I'll sketch this on the board real quick. You've got a carbon atom. I'll have to bring back my other thing in a second. You have a carbon atom and you have two O's. And just to save time here, I'm going to do this kind of quick. But the reason that I know that this is what it is the number of electrons here is 4 for this, 6 for this, and 6 for this, which is 12 plus 4, or 16 electrons in the valence level that I got to work with. Well, if you look, 2, 4, and then here's a pair, 6, 8. I'm putting dots on there so it looks like it's messing it up. But those are 8 on the side of one O and 8 on the other side for the other O. So this thing ends up with 2 double bonds on the carbon, which gives it 4 bonds, gives the O2 bonds. And if you look here on the model for CO2, it's got that. Here's the O, there's the O, here's your double bond, here's your double bond. This is what we call a 2-electron domain central atom. This double bond counts as a domain, so does the other one. So if you look at what the electron geometry is, it's going to be 180 degrees apart. It's linear, and so this molecule is called linear. In this case, those two agree with each other. Now let me go up to one of the next things up that we might have. Let me try this one, perhaps. Wait, don't know that that's what I want. Let me try. I'm looking for one that's going to be what we want here. I will have to make up my own. They don't have one that fits this. The one that I'm going to do, I'm going to turn the names off real quick. I'll sketch sulfur trioxide real quick. So here's sulfur. Here's an O, here's an O. We'll put an O down here just because I got a little spot to put it. If I count valence electrons, everybody in this has 6. O and sulfur in the same family. So I have 24 valence electrons to work with. When I start looking at that, I could go like 2, 4, 6, 8. That would work really well. I could do the same thing here to this O. Put a lone pair down there, so it's got 3 lone pairs on it. But if I do that to this O right here and use up like all 8, I could put another lone pair down here on this side of the molecule, but where that's at right there, that's going to leave the sulfur. If you count here, it's just going to have 2, 4, 6. So I really don't have enough electrons to kind of go around. So instead of having a lone pair right there, I'm going to make a covalent bond and make a double bond. So if you look at that one, you've got the sulfur with a single bond to an O, single bond to another O, and then a double bond. That is 3 clouds around the middle. So if I modeled that, I'd have like, here's one of the O's, here's another one of the O's. Notice that would be a linear molecule because of the 2 clouds. When I put that on there, I get this thing that is going to have an electron geometry and a molecule shape that are both trigonal planar. If you look here, here's the flat side, here's the triangle part. This is a flat triangle is what this molecule is, no matter which way you want to turn it. So that's where we get the name trigonal planar for that. Now I did not show you this one, but I'm going to show you something just a little different here that's based off of trigonal planar. I want to show you an example of where the electron geometry can be different. Hold on a minute. Okay, so anyway, we had a slight interruption there with a phone call. But as you can see here, I've got 3 clouds around the middle, and this is trigonal planar. I was going to show you how it's possible to have a difference between the molecular geometry and the electron geometry. And that's actually pretty easy to do. In fact, there might be a real molecule that I could do that would show this. Let me just glance here real quick. It would need to have probably, nope, that ain't what we need. Yeah, here we go. Here we go. This is sulfur dioxide. If you were to do the structure for this, and this would be good practice, if you count your electrons that are available in SO2, then what you've got is 6 for the S and then 6 for each O, so you've only got 12 electrons. You've still got to make 3 atoms happy. The sulfur in the middle and the O's. So really with 12 electrons, if I've counted right, 6 and 6, 3 6s, I'm sorry, I can't count, it's 18. If I were to do the lone pairs, this would be 2 4 for the bond, and then they don't show lone pairs on the atoms that aren't in the middle because they don't want to clutter the diagram up. But it's like this one down here where the O's, actually it's like this one right here where the O's got lone pairs. Double bond and 2 lone pairs. So that takes up 8 electrons right there. This O over here is also using 8 electrons. This is a bad example in a way because it violates the octet rule. But if you'll give me right now that sulfur actually has more electrons than it needs, it's like where are we going to put the other 2 because we've got to use 18. They got to go here. So yes, it violates octet rule, and I will stay away from that. I will stay away from that on our test. But if you look, here's what the deal is with this one. It does have a total of 3 clouds. 1, 2, and the lone pair counts, so that's 3. So the electron geometry is trigonal planar. It's still a 3 deal. But because the lone pair here has doesn't get counted in the shape, so to speak, then the molecule, you will notice, is just this shape right here, which looks like a bent shape. So that's like the first example there that I could show you real quick. It's not one that we're going to study very much. I will show you the ones here that we are going to study and need to know. But this is an example where you can have a trigonal planar type electron geometry, but you don't count the lone pairs when you name the shape, so this ends up being a bent. So let me take you through the last 3 that we need to show you here, and you'll see some more examples of this kind of thing. Okay, so let's kind of go to, I think I can pick some examples here now that will work pretty well for us. I need to stay away from a couple of these. Here's a great one right here. Okay, so what is this? This is CH4. This is methane. If you notice, the electron geometry, here's all the bonds on here. If I can get them so you can see all the bonds. There we go. You can kind of see them all. One of them's trying to hide in the back. You flip them around here. There we go. We can see them all. 1, 2, 3, 4. That's a 4 electron domain, so that is a tetrahedral. Hold on a minute till the announcements are done. Okay, so hopefully we can wrap this up. This is a tetrahedral geometry for the electrons. They're distributed as far as they can get from each other in this VSEPR theory. And because there's something bonded in all these parts, the molecular geometry is tetrahedral. That's what like the actual molecule is. It is based on a tetrahedral electron geometry. Now down below here I sketched the Lewis structure out so that you could just see that right there. And this is what it would look like if you were to sketch that Lewis structure. Here's what it looks like in 3D. Let's go to another molecule real quick. Let me bring in a Lewis structure for ammonia. And you can see that it's got 4 clouds around the middle. And it's got a lone pair. So since this one has ammonia in it, I'm just going to call that up. Now here's where you can start to see how can these 2 things be different. Let me put it to you this way. When you look at this, looking at the lone pair just like it would any other pair, do you see that here's 1, 2, 3, 4. It is an electron geometry that is based on a tetrahedron. So that's why this says tetrahedral right here, because it's still 4 clouds, and so it's still based on that same shape we just saw. But when you go to name it, if you look at the actual shape of this little molecule, he is a 3-pointed pyramid, and that's where they get trigonal pyramidal for the actual molecule, not counting the lone pair. So on a test or something, you're normally going to be asked to say, hey, look at this molecule right here, you know, or look at this Lewis structure, what shape would it have? When you see 3 clouds, okay, that are bonded and one of them it's not, you still have 4 clouds, okay? You still have 4. So it's based on a tetrahedron, but you have only 3 bonding pairs, so its actual shape is a trigonal pyramidal. All right, so anyway, last interruption I think there. Okay, let's do one more, and I'm going to drag in a Lewis structure that I have already drawn here. So let me move this one over here, move this one over here, and make some room for our friend water here, H2O. There are 6 valence electrons on an O, and there's 1 each from the H's, so I have 8 electrons to play with. So I have 2, 4, 6, 8. The O is happy, I use the right valence electrons, and the H's are happy. So I can call up a 3-dimensional model of H2O. And I'm going to turn it like this if I can. Now, here's what I'm saying. This is a 4 cloud on the central atom deal. Okay? 1, 2, 3, 4. So it's based on a tetrahedron. That's its basic thing that is governing it. But what do we call the shape that has 2 lone pairs and 2 bonding pairs? And if I turn it in our Mickey direction here, you can see maybe why the molecule is a bent shape. So as a quick review with all 3 of these Lewis structures that we have here, this one, which is our first Lewis structure down here, is a true tetrahedron all the way around. It's got 4 bonding pairs, no lone pairs. That's going to be a tetrahedral molecule. The next one, which is this Lewis structure for ammonia, is still based on a tetrahedron because it has 4 clouds. But this one has a shape of trigonal pyramidal because of the shape of where the bonds are here. And then finally, going to this last one, H2O, this thing has 4 clouds around the central atom, so it's based on a tetrahedron. But what do we call it when only 2 of them are bonded pairs and 2 of them are lone pairs? And the answer to that question is that's a bent shape. So to summarize, the only ones you're going to have to learn as juniors are these. If you have 2 clouds, you're going to have a linear molecule. If you have 3 clouds around the middle, you can start getting into some of this, but we're going to try to stick to examples where we have 3 clouds where everybody's bonded. And so you can get trigonal planar. The other possibility that I'm not going to expect you to know right now is you can get a bent shape from that too. This was the example right here. The way this thing bonded, it had 1, 2, 3 clouds, but it only has a bent shape because there's nothing bonded up here to contribute to part of the shape. Don't worry about that one. When you get to the tetrahedrals, you need to know that it can be tetrahedral if they're all bonded. It can be trigonal pyramidal if one of them is lone and the other ones are bonded. And it can be bent if you have 2 lone and 2 bonded. All 3 of those last ones are based on tetrahedral geometry, but they are different shapes if they have a certain number of lone pairs. So I hope that little summary helps a little bit to, just to give you something to look at there to make that a little more clear. When you think about it, you're really only being asked to learn about 5 things here. In AP chemistry, we could get into more. Not a ton more, but there's at least 4 or 5 more that are fairly common. So I hope that helps, and catch me at school or whatever if you have any other questions I might be able to answer.